Yeah. It isn't pretty much like, so, for instance, this equation, use height of volume. So I would pick a variable that makes sense. Like you could literally write out in this case, sorry, you could literally write out volume as speed. Generally, it's just a kind of, it's not actually quite necessary, but you do need to use like slope. So slope 1.7.
Yeah.
Here it actually put it. Your x is height, so you can use whatever variable as long as it's kind of makes sense. So you leaving it as x would be a good idea. Maybe h is height, something like that. And then y-intercept.
I appreciate it,
Yeah.
and then I'll take this equation and kind of put it together in reference to what we're actually working, which is wavelength and energy.
Yeah, so,
Is it
so,
just-
so for length 6, when we write the equation that you're supposed to be using, or is
I have
this
that.
flat 5, it's the same idea.
Okay, thank you.
I remembered that this existed, so I just wanted to show you this. It's interesting, kind of. It's very dim, probably from where you're sitting. You can kind of see the 4 spectral lines for hydrogen. That's the one we're very familiar with. One of the flaws of this is that not every wavelength of light here is actually equal intensity. And so they've actually played with the intensities quite a bit. If you were to look at the sodium spectrum, you would really only see the 2 yellow lines, and that's it. The others exist, but they're so dim compared to the 2 yellows that you couldn't really see them. So they played with a lot of the, I wouldn't say the contrast, but they played with the intensities so that you could see more. But yeah, it's interesting. And these are, this is kind of proof that every element has its own fingerprint, basically. You can identify elements based on their emission spectrum. So it kind of looks like a big, all the same, but there are very different, there are differences between them, even ones that look very similar. So, all right. So we started talking about photoelectron spectroscopy. And I think we're going to look at some real examples in a second after reviewing it, and then we're going to revise our model, and then kind of take it to the next level and talk about electron configuration. So, just to make sure everybody understood, the experiments we've been looking at before are just simple ionization experiments. We've taken an atom, we bombard it with high energy electrons, and those electrons transfer some energy to the atom, cause the atom's own electrons to leave, to ionize. But that technique only allowed you to ionize a valence electron, the easiest to remove electron. That's it. You couldn't explore the inner electrons with this technique. So we need a new technique, and that's photoelectron spectroscopy, PES, sometimes called XPS as well, X-ray photoelectron spectroscopy. Get straight off. So if we know the energy of the light that we're hitting our atom with, we can calculate the ionization energy of the electron that has been ionized. It's a fairly basic equation. So HV, this is the formula for finding energy of a photon, right? That's going to be an X-ray photon in this case. And then this kinetic energy is the kinetic energy of the electron that's left. Like we've ionized an electron from an atom, there's an electron flying off in space. The speed at which it's moving is can be converted to a kinetic energy. That's energy of motion. And put together, we can use the speed of the electron flying off to figure out what its original ionization energy was. How tightly was it being held by the atom? Was it a really high ionization energy? It was like really deep in there? Or was it a low ionization energy? Was it one of the valence electrons? So that's kind of what we did. We're actually looking at. And so this is the machine. This is the basic setup. We saw the video. It's just a monstrous thing of metal with a computer attached. And
like an alien.
Yeah,
Or a robot.
These setups could be used for lots of different things. Photoelectron spectroscopy is one of them. Growing diamonds, there's vacuum chambers are awesome if you get to play with one, and of course lasers are too. So it's they're both fun to play with if you know what to do with them. Okay, so we covered this. I'm going to skip this real quick, and we covered this. This was our simulated atom. What do we see? If we were to kind of generate a graph of ionization energy versus electrons ejected. And so this is what we saw. I think the conclusions we came up with were that the height of the peak cannot be used to tell us whether or not, actually, well, we haven't talked about that. We'll get to that in a second. But we can tell ionization energy based on scale. We also did this one, where we had a slightly more complicated atom with 5 electrons, 2 different energy levels. We concluded that, we would see 2 different peaks. Because let's say that this is the 0 energy, it would take this much energy to ionize the 2 down here, right? This distance, a big ionization energy. These would take less energy because it's closer to 0. And there'd be a ratio in the peaks of 2 to 1 based on the fact that there's 2 versus 3 electrons. So we can get a lot of information from these things, theoretically. We did that. What we haven't done is now, let's look at some real data. So this is page 168 in Chem Activity 8. Let's quickly just do 12 and 13. So this is an actual atom, but an unknown one. And let's see what we can figure out from this. They will get harder. This is pretty simple. They will get a lot harder. But you'll figure out it's not that bad. Get used to it. Well, so in the last one, we figured out that if we had more than one peak, the multiple peak could tell us the ratio. But if you only have one peak, there's no way to figure out a ratio.
Okay.
So that peak could be 1 electron, 2, 3, 4, 5, it's hard. It's impossible to know.
So because we don't know how many electrons.
Mm-hmm. maybe this is Kortchart model, but like the original shell model, how many
Yeah,
shells?
yeah. And that's like looking at the data and I was like, this is
This
pretty
has
cool
two,
that-
right? So the first shell has 2 electrons. The second shell has 1 electron. The second shell electrons are they're going to be different ionization. So lithium should have 2 peaks according to our.
I was looking at it and I was like,
Yeah.
trying to figure out what number it is. Until I thought.
Yeah, 1 for each shell. Okay. Let's talk about the answers. So we're just kind of orienting our brains to make sure that these start to make sense. We can think about these critically. So why is it not possible to determine if this is hydrogen or helium just from the graph itself? I mean, it might help to kind of visualize what exactly is happening in the machine. You're shooting a beam of, in this case, it's either hydrogen or helium or something, towards your X-ray photons. And, you know, when this photon hits a proton, a single electron comes out. And then it just keeps going, right? It's done. And the next turn is the next atom, and then that gets ionized. And the next atom, that gets ionized. 1 electron is coming out of every single atom. Now, the peak is as large as it is because the detector keeps detecting, oh, an electron's coming out with this energy, It's the same energy every time. And it just gets bigger and bigger and bigger. But there's no way to tell if that atom had 8 electrons or just 1. Versus, you know, never mind 1 or 2. So unless you have a second peak there to compare them, there's really no way to know if that represents 1 or many electrons. And even if you had 2 peaks, remember all we can see is a ratio. So if it's a 2-to-1 ratio, it could mean there's 1 electron and 2 electrons, or it could mean there's 2 and 4, or 3 and 6. We still don't know the exact numbers, okay? We can make some educated guesses about it, but so we have no idea if it's hydrogen or helium. We can't know it's lithium, or we know it's not lithium, right? Because lithium has 2 shells. We know that from our current model. And so the electron in the second shell of lithium should have a different ionization energy. Or maybe that's the second shell, and the first one should be harder to remove, higher ionization energy. So we should see 2 peaks. It can't be lithium. Anybody looked it up? What is that? What does the ionization energy tell us about the identity of this atom? It's helium, yeah. So this 2.37 is the exact same energy that's listed in the table for helium. So on these, well, okay, we'll come back to that. So ionization energy, the original table that we looked at, is related to these photoelectron spectrums, okay? We just get a lot more information from these photoelectron spectra. Maybe not this one, but in future ones we'll take a look. We'll see more information. So, the peak height is proportional to the number of electrons, okay? So if hydrogen has 1 peak, helium is also going to have 1 peak. It's going to be double the intensity, but I can't see the difference from a regular graph, okay? Lithium should have 2 peaks. There's 3 electrons. 1 should be double the other one, right? Because it's going to be 2 versus 1. And this is the kind of the relation to what we've studied in the past. While photoelectron spectroscopy can give us many, many peaks on the graph, the lowest energy peak is still going to be that ionization energy that we originally studied, right? The definition of ionization energy, especially the one here, the first ionization energy, is the amount of energy it takes to remove the easiest to remove electron. So that's always going to be the same as that lowest energy peak on your photoelectron spectrum. I mean, that's why that number matched up with your table. Okay, so now let's look at some real data. Well, more real data. This one's more interesting. And actually, before we look at the data, let's predict what it should look like. So, we have the shell model of neon, which you're familiar with. This is our trusty model that has been working for us so far. let's answer questions 1 through 3 on page 172. And the next kind of activity. Basically, in the end, you're going to predict what the photoelectron spectra looks like. For what you think it should look like based on what we know so far. Okay? 1 through 3. So based on this, what should photoelectron PES spectra look like? When you're ready to draw the spectra, I'd just remind you there's a quirk of these spectra that the ionization energy on the x-axis increases going to the left. It's just how they do it. So don't forget that part. You're going to see a lot of these, so you'll get used to it. Yes.
So-
Yeah, the larger energy.
So these would be the first peak.
Yeah.
Yes.
And that's at 2.08. And I don't know if the ratio is 2 to 8.
You're right. It is 2 to 8, same as 1 to 4. Yeah.
So I figured that we don't know what this energy is,
Ah.
but it would be a lower energy because the distance.
Okay, so first, they're saying that this 2.08 is the first ionization energy. So that's going to be the lowest energy possible.
The ground.
Not the ground state, but it's the energy required to remove the easiest to remove electrons.
Okay,
So anything else is going to be higher than that.
So this is this one right here.
It's the big peak, yes.
Is the big peak.
Yep.
Okay.
Because you're removing the outer electrons. Yep.
Is that relative to the nucleus or to 0?
It's probably not very.
What I have here is higher energy, but the distance from 0 is much
So, well, don't use, well, distance is a way to stop fighting about it, but, I mean, think about it, the closer an electron is to the nucleus, the more attractive it's gonna be.
Yes.
Right, so the more energy I will need to put in to break that attraction.
The smaller peak is the higher energy because
Well, I would say, so the smaller peak corresponds to the two inner, right? Because that's why it's smaller, there's two. And the inner electrons are higher energy because they're closer to the nucleus.
correct. And we know at this one.
That's going to be the lowest energy on your diagram. Because the first ionization energy is defined as how much energy do I need at a minimum to remove an electron. And the first easiest one to remove is going to be one of these outer ones. These inner ones are going to take a lot more energy. So 2.08 is the minimum because one of these is combined.
Okay.
Okay, I think we've talked about it a little bit. Some of you have the beginnings of a diagram. So how many peaks? 2? What's the ratio? 1 to 4, 2 to 8, same thing. Yep. And you can get that just by number of electrons in each shell, 2 versus 8. And that's the reason why there's 2 peaks, there's 2 shells. So the next part, you'll have to organize, your data in your head. We're giving you one of the energies, 2.08. That's the first ionization energy. That is going to be, over here, the lowest energy on your diagram. That is what the ionization energy is. It's the minimum amount of energy needed to remove an electron. That's going to be the lowest one. And then the other one's going to be somewhere over here higher. We don't know what it is yet. Somewhere over there. We don't have to be accurate about scales here. And when we draw in which is which one is the high one, which one's the low one? Which one's the 4, which one's the 1? So here goes what?
Low. That one's the big one.
That's the high.
This is the big one. So why is that? So if I do 1, 2, 3, 4, that's about right. Well, that's because the easy ones to remove are the outer or the valence electrons. And that's where there's 8 of them. So these are the ones that have the really low ionization energy. Those are easy to remove. They're furthest away from the nucleus. They're shielded by the inner electrons. They are less tightly held on. So they have the lowest ionization energy. And then the next 2 have the higher ionization energy. And they're in a ratio of only up to 1. So 1 to 4. That's kind of what we expect it to look like. So far so good? Yeah, all right. Okay. Surprise. Doesn't look like that. All right, so this is what neon looks like. I think you can see the differences, but might as well answer the questions and have it written down somewhere. So look at questions 4 and 5 on page 174. Just quickly kind of sketch out what you see, or not sketch what you see, but think about what you see, put it in words, and see if we can explain it. So this is obviously, there's something wrong with our model. Our shell model is not working, because it doesn't predict this. ratios can help in this case. If not ruler, just something, you know, your thumb, if you want to just kind of eyeball how big these are. Okay. Anybody figured out some of this electron stuff? So let's answer 4A real quick, 4B. So, is it consistent? No. It doesn't match. It's supposed to be 2. This has got 3. How was our prediction correct and how was it not correct? Well, we got the wrong number of peaks. But we did guess that the big peak was the low energy one and everything else was higher. Yeah. What you may not have noticed are the ratios are different. And this is why it's nice to have a ruler. If I measure the height of the large peak here, well, let's actually measure this short one first. So the short one is just about 20 and a half centimeters. If I measure the tall one, it's just about 60 centimeters. So 20 versus 60, that's a ratio of 1 to 3. This peak is 3 times higher than this one. And this is exactly the same height as this one. So the ratio is 1 to 1 to 3. That's how high they are. FYI, if you have taken calculus, we would be better off doing area under the curve. But not all of us have done calculus, so peak height is enough. It's good enough. So 1 to 1 to 3. How many electrons is neon supposed to have? 10. 8 valence, yes. 10 total. So 1 and 1 and 3 add up to 5. It's not enough. So if we double everything, 2, 2, and 6, that adds up to 10. So that's what these peaks represent. 2 electrons here, 2 electrons here, 6 electrons here. That's all of the electrons in neon. So when you hit a stream of neon atoms with X-rays and you analyze all the electrons coming out of them, there's 3 different energies. And we get these ratios because of probability. You know, when you do it enough times, you're going to have more of these electrons because there's just more of those electrons in that shell. Yeah.
So, is it not how many shells they have, just the number of peaks?
Sort of. So basically, our shell model is not perfect. There's something wrong with it. It's not predicting this. So we have to refine our model. And the way we're going to do it is, I'm not going to make you guys come up with it this time. We're going to just tell you how we're going to do it, which is this concept of subshells. So now shells are split into smaller categories, subshells. And I really don't know the history of why they picked the letters that they did. I feel like it must be something German related. but I can't remember exactly what it is. It's not a big deal. But we use these letters to represent these subshells. So the first subshell is called an S. The second one's called a P. The third one is called a D. And the fourth one is called an F. And they technically don't stop. You can have more than this. But these are the only ones that matter, okay? So how do we now define where an electron is? So before we said the electron was in the first shell. It's not enough. We need to now include the subshell. So we would say hydrogen has an electron in the 1s subshell. So 1 represents the shell, S represents the subshell. So it's in the 1s. It's an address, basically. So helium has 2 electrons in the 1s subshell. Lithium and beryllium, those are the next 2. We would add those third and fourth electrons into the 2s subshell. Now, again, we're not going to get into the origin of the S and the P and the D and stuff. And we're not going to go through all the data to kind of prove that they exist. But this model is now going to fit with the data we're seeing. With, like, for instance, neons, which I don't have on the screen. Neons put an electron spectrum. So once you get past the 4th electron, the 5th electron is now added to a new subshell that's in shell 2, called the 2p subshell. So not every shell has all the subshells. So it looks like the first shell only has S. The second shell has an S and it has a P. And that's it. It gets complicated, but we're going to learn a way to memorize, not memorize, but learn a way to come up with all of these subshells and what exists and what doesn't, and what order they're in, and all that stuff. So again, we're going to use something called an electron configuration now to kind of map out where the electrons are. So before we used the shell model, we had our little rings around the nucleus, and it worked because it was a simple model. You didn't get too crazy. Of course, once you start putting 5 shells, it's a lot of circles, it's a lot of dots drawn in. So even that got crazy. But if you start adding the subshells, all those circles are going to get too crazy to draw. So another system, an easier system, instead of being graphical, we're going to use this. And so, again, the number is the shell, the letter is the subshell, and in superscript notation is the number of electrons that are in that shell, that subshell. So that 2p subshell contains 2 electrons right now. That's how we're going to do this. You would just string those along. So you're going to have a number of electrons in the first subshell, a number of electrons in the next subshell, a number of electrons in the subshell after that. So this is the electron configuration for hydrogen. 1s, 1. 1 electron in the 1s, that's it. Helium is 1s2. There's 2 electrons in the 1s subshell. Lithium would be 1s2, 2s1. That means 1 electron in the 2s, 2 electrons in the 1s. Carbons, 1s2, 2s2, 2p2. That's just how we're doing it. This is an address, basically, where all the electrons are in the atom. Okay. So we're going to get to how you can write this yourself without having to memorize anything. So here's a little bit more. Yeah.
I didn't end up being able to grab all of the names of the subshells.
There's the S, the P, D, and F.
S, P, D, and F. Thank you.
We'll come back to those soon. We're kind of introducing it now. So let's see. What does this solve for right now? Well, first it solves the whole photoelectron spectrum that we just saw for neon. It also solves a few things that we saw on, for instance, this chart. So when we looked at the ionization energies, we followed the periodic table. As you go from left to right, ionization energy goes up. Left to right, ionization energy goes up. When you go to the next row, it drops, right? We know why. But there's all these little blips in here that kind of don't conform to the trend, right? So here's one. beryllium to boron. Why, when you go across the period, which you expect the ionization energy always to go up, but when you get to boron, it drops down a little bit. Why? Well, now we can see maybe why that occurs. The electron configuration of beryllium, 1s2, 2s2. The next one, boron, is 1s2, 2s2, 2p1. It's lower, the ionization energy is lower because that next electron is actually not going in the same subshell. It's going in a different subshell. That implies maybe that subshell is slightly further away from the nucleus than the 2s subshell is. And that's why the 2p subshell is lower, or the ionization energy, I should say, is lower in energy. So, you know, this new model is already giving us clues as to why we get these little deviations in our trends, you know. We haven't gotten to this one yet, but here's another one where you get the S to the P transition. So magnesium, the electron configuration, the last part of it is 3s2. And then when you get to aluminum, you don't put that third electron in the 3s, you put it in the next subshell, the 3p. And that's why it drops a little bit.
So after, when there's 3, we move it to the next one?
We'll come to like the pattern. So the S electrons the S subshell can only hold 2 electrons, and that's it. We'll come to that. We'll come back to that pattern, but yeah, S subshells can only hold 2. P subshells can only hold 6. But I'll show you a better way to memorize that. It's your periodic table is going to be your cheat sheet for that.
And you mean by 6, you mean electron?
6 electrons, yeah. So before we get to this, I think we can just do this together. We have chem activity 9 on page 175. We'll do questions 6 and 7 together. So let's get to it real quick. So coming back to the neon atom, there's a lot here. But what is the reasoning behind the assumption that the peak at 84 megajoules per mole corresponds to electrons and the n is equal to 1 shell? So just coming back to it real quick. This peak corresponds to electrons in the 1s subshell, or shell 1 even. Why is that? Well, these are the inner electrons. Inner electrons are going to be super tightly held on. They're going to have huge ionization energies because they're feeling the full force of that nucleus, those protons in the nucleus. They're feeling everything. These are valence electrons. These are further away. They're shielded by the inner electrons. They don't feel the nucleus as much, and that's why the ionization energy is so low. Okay, what was the other one? 7y, on the information provided, why are two of the 3 peaks assigned to n is equal to 2 shell rather than n is equal to 1? So now using our new model, these are both shell 2, but these electrons are from the 2s subshell. These electrons are in the 2p subshell. And so using information from this, we can kind of glean that, well, the 1s can hold 2 electrons, the 2s subshell can hold 2 electrons, the 2p subshell can hold 6 electrons. So anyway, just kind of showing you that this new model I'm introducing to you fits this data very well. Yeah?
So 4.68 and 2.08 are both in the second?
They're both second shell,
Second.
but they're different subshells. So this is the S subshell. This is the P subshell. So we just say it 2S, shell 2, subshell S. 2S, this is 2P.
Wait, sorry, so is the first one 1s?
1S, yes.
So this is almost an evolution of n equals 1.
It is exactly that, yeah. We're going to get to that. That's complicated because when we studied the whole n energy level, that quantum number thing, we only really did look at hydrogen. And hydrogen is a unique atom in that it only has 1 electron. So for 1 electron systems, you actually don't see the subshells. It's a weird, it has to do with electron-electron repulsion. Once you have more than 1 electrons, the subshells, they become very apparent. So studying hydrogen was kind of a blind spot, really, because we didn't get to see all this interesting stuff happen with the higher level atoms. Yeah. So there's such a thing as being too simplistic. All right. All right, so that's it for that. So here is, let's kind of play with the electron configuration and these ionization energies, photoelectron spectra energies a little bit. See what kind of information we can pull out of these. So this is what one I'd like you guys to do. Chem activity 10, page 179, questions 1 through 6. Just kind of look at the data and see what you can glean from it.
What am I doing here? I'm looking at this and I'm thinking we're talking about this, but it's asking for the state.
So n, remember, is the quantum number that refers to the energy level, or just the shell part. So it is shell 2, like you think.
Okay.
We don't need the subshell at this point, just shell 2.
Okay. And because there is 2 shells in
And the valence shell is the outer one. Yeah.
Yeah.
Yep. All right. So the n here, if you go back to connectivity 7, I think that's where we introduced it. N is a quantum number that we use to refer to a shell, the shell number. So it's the same as the shell. So this is shell 1. These are both shell 2. They're just in different subshells.
And this is the right one, so last one.
I didn't realize
Yes.
that there was a 300 at the end. So it is. So if I'm looking at this one, I am looking for the
Mm-hmm.
It's going to be the easiest, the lowest energy one. Yeah.
Yeah.
But this is without saying anything about the subshells. We're looking at the subshells, but
Yeah, right now we're just getting like really basic information. This is
What's the number of electrons?
we're not taking advantage of all the rest of it.
Yes, that's what I said. It's like, there's 200.
just, that was funny. So what I'm looking here
And
is, this is the electrons, like how many
Mhm.
electrons were emitted, so I'd be doing
the check
two,
presents the,
two.
oh, is that what you're saying? You changed it?
And, I mean, you're looking here, which is fine.
Is it,
Right.
so the second shell is
Because
the
they're,
I'm sorry.
and then
I've
the
got
third
the-
shell is your
I got that too.
perfect, yeah. So,
two and the
are
third.
they, this gives you, this one,
Right.
this gives you numbers, this gives you, yes.
Yeah, that's fine. That's a final shell. So that's why it's the second shell.
Okay.
Since there's two and the remaining electrons from the second. Because they can have a maximum of 8.
Perfect, all right.
So, dashes represents which shell is the valence shell. So, second shell in nitrogen is the last shell, our final
We'll get to that. So that's when we introduce the quantum mechanics part of it.
I still want to.
Our simple idea of a particle orbiting like the sun kind of thing, the planet, that's what we're doing now, which is not quite right, but it works with the model for now. But again, yeah, we're going to introduce that next. Yeah.
Just a quick question. This sort of looks like would this represent the light spectrum that we see when we do diffraction? Like, it looks, it kind of looks like.
It's not the same as the visible part. Think of this as the energy level turning sideways. So like the bars that are going this way, and then you kind of plot, hey, electron goes from here to here. That's that part, just turned sideways. So it's more like this. So that's energy level, the lowest energy level. And then that's the next.
So
But
this
then,
would be N.
yes, but now we're making it more complicated. It's no longer a single N2, it's two N2s together. There's a 2S and 2P.
Okay.
So we're splitting the energy level now. We're making it a little bit more complicated.
Okay.
Yeah.
But can it do that?
Mm-hmm.
Because what we were originally saying is it jumps from like 1 to 2.
Exactly.
But we have, now that's what we're doing. We're
Our
changing.
model, though, was based on hydrogen, which is a really simple atom with only one electron. And yeah, when you use hydrogen, that works perfectly.
One's gonna equal.
But I did say that the Bohr equation, the equation for calculating energy levels, didn't work as well for anything else besides hydrogen. And this is why, because you start getting multiple electrons, you get these subshells.
So this would be like N2 and this one, let's just say N subshell 2.
Well, they're both N2.
Oh,
It's
they're
just-
both N2.
There's different subshells.
The subshell, the second one's P?
Yeah, there's a 2S and 2P. Yep. So the N thing, we're gonna learn that the N is just for the shell number, both N2. The subshell is a different one that we're gonna learn later.
Okay.
Yeah. Give it. Yeah, 5 feet.
Oh wait, it is, yeah.
So
It is.
the numbers here are the shell number, it doesn't tell you how many electrons.
Yeah, 'cause I was noticing, this has 6.
Yeah, so down here it tells you how many electrons. Down here.
I mean, it's pretty cool.
Well, so there's gonna be ratios of like 1 to 3, because if you look here, it's 6 to 2, it's the electron 6 to 1 to 3, yeah.
Yeah.
That was kind of what I.
I mean, you know.
So you're close, you're close. All right, let's talk about the answers real quick. I think everybody got this part fine. The technique, photoelectron spectroscopy. The photoelectron spectrum of argon. You can use both pieces of information. You can use the electron configuration. That kind of tells you how many electrons are in every peak. And in combination with the photoelectron energy. So the other chart tells you not how many electrons, but what the energy is. So this and this together are going to let us get our photoelectron spectrum. So you're going to have a one peak down here at 309. You're going to have another peak way off separated. I'll put a big break. That's the whole hash mark we use to indicate there's a big break in our axis. So there's a 31.5 peak, and there's a 24.1 peak. And then there's another big break because, you know, it's far away. 2.82, yeah. And a 1.52. So those energies tell me the positions of my peaks. This tells me the number of electrons. 2 to 2 to 6 to 2 to 6. That's the same thing as saying 1 to 1 to 3 to 1 to 3. So this is a 1. The next one should be 1 as well. The next one, 6. This one's 1. And then this one's 3, not 6. So 1 to 1 to 3 to 1 to 3, 2 to 2 to 6 to 2 to 6, same ratio. And just in case you're curious, I didn't show the whole thing. I mean, we've got the labels for the subshells at the top of this thing. So it's literally telling you which one's which. So this is the 1s subshell. This is the 2s subshell. This is the 2p. This is the 3s. And this is the 3p subshell. Yeah?
So will you always get that ratio there at the end, like that last ratio?
This part, well, so for noble gases, the subshell and the shell is filled up completely. So it's only for noble gases where you get this perfect ratio over here. For something like chlorine, there'll be one fewer electron over here. And so you would have it would be half as high. Not half, it would be a ratio that was 1 to 2.5 or something like that.
Sure.
Yeah.
But on the left side there, it's always going to be.
These are going to be full, yeah.
Okay.
So, yeah, they're going to be full. The inner electrons are full, the inner shell, excuse me, are full of electrons.
Cool.
It's only your valence shell that's going to have varying numbers of electrons. Yeah. Okay.
So just to be clear, the ratio is 1 to 1 to 3 to 1 to 3.
Yes. Yeah, and that's based on the electron configuration for argon, which is telling you there's 2 to 2 to 6 to 2 to 6. We look at the superscripts. So the big coefficients, the big numbers, that's the shell number. The letter is the subshell, and then the superscripts are the numbers of electrons in those subshells. Oh, I think I forgot something. Let's see.
Number 6? Did we do number 6? Did we already?
No, we didn't, I think. Is it possible to deduce the electron configuration for an atom from its photoelectron spectrum?
I would say yes by
Yeah.
using the ratio.
So, well, I mean, without knowing that this is 1s and 2s and 2p, could you come up with this from just, you know, the peaks?
I think you could because the ratio 1 to 1 to 3 to 1 to 3.
Yeah.
I think you could.
Yeah. You haven't seen enough of these, but we saw neons. Neon had a similar pattern. It always started at 1s. They all start from the same beginning. They all have the same pattern order. It's just towards the end is where it matters. It changes because they run out of electrons, so you can't fill it all the way. Definitely. You can totally get one of these things from just that photoelectron spectrum.
Based on its pattern and ratio.
Mm-hmm. Yeah.
Is it normally doubled? If you see peaks that go to 1 to 1 to 3 to 1 to 3, do you normally need to like
yes.
estimate
So
that
what we're gonna
double that?
we're gonna eventually learn. Well, we'll learn now. The S subshell holds 2 electrons always, maximum of 2, I should the p subshell holds 6. The d subshell holds 10. The f subshell holds 14. And I'll repeat those again later.
Okay.
So it's you'll but they're constants there. Okay, so if your smallest peak over here, if there's more peaks, that's always going to be 2 electrons. Always going to be 2. So just know that, and you can get everything else from that. All right. So here's an example of what we were just telling you. Was it possible? So what element do you think this photoelectron spectrum is for? And I know you guys don't know the subshell ordering, so we've got a little table down here that might help you. You could just go by the numbers too.
That's what I did.
Mm-hmm. All right. Not too fast.
The numbers.
You can change your answers too. All right. So most people said A. One person said C, and I know why you said C, which is it's understandable. But the answer is A. So first, a few features out of this that you can kind of pick out. Like I said, that's your lowest subshell. That's the 1s. Or is it? Yeah, it's got to be. That has 2 electrons in it, so that has 2. If you measure the scale here, this is 3 times as high, so that's 6. That's got 2 electrons, same as this one. That's 6. What's this one? How many electrons in there?
I'm gonna guess
1. It's half as high as this. This is 2. If this is half the height, that's 1 electron. That's going to be a clue, and like I said, we're not quite ready to do this yet, but if you look at the numbers, the energy is 347, 347. I mean, it fits potassium pretty well. Somebody who said scandium, the pattern makes sense a little bit for scandium, but scandium should have 1, 2, 3, 4, 5, 6, 7 peaks, and there's only 1, 2, 3, 4, 5, 6. So there's missing a peak. It's not scandium. SC. Okay. Yeah, question.
Why do potassium and calcium skip the 3D subshell?
That's because the 3D subshell is higher in energy than the 4s subshell. So when you fill your atoms with electrons, they want to go in the lowest energy subshells possible. And so that 19th electron goes in the 4s, because the 4s happens to be a little bit lower in energy than the 3D.
How many electrons does the D hold?
10. 10 total. So what's happening here is calcium is the 20th electron, still goes in the s, but then the 21st electron, there's no more room in the s. So the next is the 3D. That ordering, I'll show you how to memorize it without memorizing it. It's not hard. So yeah, so there it is. So this is the old school way of doing it, and I learned this a long time ago, and I still remember it. So it works. It's a little tedious. So to memorize the subshell orders, which is what this is showing, 1s, then 2s, then 2p, then 3s, then 3p, then 4s, then 3d, then back to 4p, then 5s, then 4d. So how do you memorize that without going crazy? So one way to do it is you can just draw a table out like this, put the shells in rows, 1, 2, 3, 4, 5, 6, 7. You do the subshells in columns, and you kind of have to know the first shell only has S. The second shell only has S and P. The third shell only has S, P, and D. And the fourth shell is where the F starts. So just set up your table like that. Then you go start from the top right and go diagonally down to the left. And every subshell you go through is the next one in line. So 1S first, then 2S, then 2P, then 3S, then 3P, then 4S, then 3D, then 4P, then 5S, then 4D, then 5P, then 6S, then 4F. It's a little crazy, but I still remember this. This is one that I learned a long time ago, and I still remember it, so it works.
Could you leave it up for just one
Yeah.
second?
There's a better way, though. I like the next way much better. And so you can come up with this ordering from there without having to memorize them. Just have to memorize the way to do it. That's all.
Just one quick second.
Yep.
So why is there no D or F orbital in 6? I mean subshell in 6 and 7 there? It's too big at that
It
point.
is mathematically impossible. That's all I can tell you.
Oh, I see.
Um,
I don't math.
So until we talk about where the subshells come from, it's kind of hard to answer that question. So it's just at shell 1, the only possible subshell is an S subshell. At shell 2, you can have an S and a P, and then it keeps going up.
You can change it.
Okay. But it's, yeah, the real answer is mathematically impossible. It's the way.
Well, math isn't real though.
So I'll give you a sneak preview. Electrons, which we think of as particles, they're matter, actually don't behave like regular particles. They behave like light does, like waves. And when you apply wave dynamics, like you treat an electron like a wave, then there are limitations to the way it can behave. And so when you apply wave dynamics to it, you get results like this, where this is impossible. Like this state of an electron is impossible. So you can't have the P subshell in shell 1 because of that. So like we're gonna have to get into what P really means, what S really means, but we haven't gotten there yet. Okay. So this is the way I like better. What you're seeing here is a form of the periodic table where the lanthanides and actinides, this bottom 2 rows, have been inserted right here where they actually should go, right after 56, 57, 58 right here. These actually should be right here, but whatever. And the reason it's showing like this is because in your head you should be thinking of the periodic table in blocks. We have our S block, the first 2 groups. We have our P block, which is the right side main group area. And then we have the transition metals, right in the middle. That's the D block. And our lanthanides and actinides are our F block. So the block names correspond to the subshell. So one other thing you have to keep in mind in your head is that helium, which is normally over there on the periodic table, just think of it as being right next to hydrogen. It's part of the S block technically, okay? Now, once you've got that kind of envisioned in your head, you don't have to think like this. There's another version I'll show you in a second. To find an electron configuration, you, let's do for bromine. Let's do a simple one first. Let's do sulfur. So if I wanted to write what the electron configuration of sulfur is, I would start from the beginning. So hydrogen, and I would say, well, where is hydrogen? Hydrogen's in the 1s block. 1 because it's period 1, and it's the S block. How many electrons can the S subshell hold? Well, this is another clue that the periodic table gives us. How many columns are in the S block? 2. There's just 2 columns. These 2. So there's a max of 2 electrons that fit in the S subshell. All right, after hydrogen and helium, there's nothing left. We go to the next period, period 2. And what's the first block in period 2? The S block again. How many electrons? 2 max, okay? Alright, after beryllium, what comes next? We get boron. That's the p block. Shell 2, p. How many total electrons can the p block hold? How many columns are there? 1, 2, 3, 4, 5, 6. 6 electrons. Alright, and that's it for that row. Next row, row 3. S block again. So 3s. And 2 max electrons. Alright, we're getting close to sulfur. So we've gone from magnesium, now we're in aluminum, and we're in the 3p block. And I'm not going to write 6. I'm going to count over 1, 2, 3, 4. I hit sulfur. There's 4 electrons in that p subshell. That's it. That is the electron configuration for sulfur. The order is correct. The number of electrons is correct as well. I like the periodic table. It's a nice cheat sheet for doing all this stuff. You're welcome to do the table thing that I showed you before, but this is better.
Can you explain like why it's 3p4 again? Why is that?
So remember that the electrons up here, the superscript, represent where all of the electrons in sulfur are. Sulfur has 16 total electrons. So 2 and 2 and 6 is 10, plus 2 is 12, plus 4 is 16. You have to have the correct number. So the inner electrons are all going to be in the lowest energy subshells possible. That's these. And our valence electrons, which is sulfur's got 6, it's in group 6. The valence electrons are going to be in the last outer shell, shell 3. But they're split up between the S subshell and the P subshell. And you can kind of, like I said, you can figure out quickly how many are in each by just counting. But we're filling up the S. So there's 6 valence electrons. We fill up the S, that's 2 max. We have 4 left. So the P is going to have up to 4, and that's it. It can fit 6, but it's only got 4, because that's all there is left. All right, I'm going to do a little bit harder one now. Let's do iron. So, same idea. Start from the beginning. And this is going to get tedious and repetitive. You'll see the pattern. You'll be like, oh, this is easy now. So, from the beginning, 1s2, 2s2, 2p6, 3s2, 3p6. I did that quickly, but like I'm going to iron. And 3p6 is this whole group here. So after 3p, next group, 4s. That's full. Now here's the tricky part. For this method to work, when you get to the D block, which is what we're hitting here, you have to remember to go down by 1 for the shell number. So it's 4s, but it's not going to be 4d. We're going down 1, 3d. So for D, you subtract 1. For F, you subtract 2. So that's going to be 3d, how many? 1, 2, 3, 4, 5, 6. So 3d6, that's the electron configuration. Let me do one more. Europium. EU. So we have a lot of boilerplate, okay? 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Alright, so I'm here now. This whole thing is filled. So how many total electrons can you put in a D? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The periodic table tells you. 3d10. After 3d, it's the p block. Don't forget, it's back to 4. We're in row 4. So 4p, 6. All right, and then I'm going to keep going. After that is 5s2, then 4. Remember, drop down 1 for D's, 4d10, 5p6, Oh my god, alright, then it's 6. Period 6. 6s2. Alright, now this is where I don't really like this periodic table, but this actually should be here. But after the 6s, you get to the F block. And I think maybe your periodic table is maybe better, but the lanthanum and actinium should be here. So when you count over, it's 1, 2, 3, 4, 5, 6, 7. 4F7. So remember, drop down 2 shell numbers for F blocks.
And the reason you drop down 2 is just to satisfy the or the things that we observe in real life.
Well, yeah. It really is in shell 4.
Sure.
The reason it's way up here is it just happens that the 4F energy is pretty high. So it's, even though it's a low shell number, the 6s is lower in energy. So that's why we would write it first. So that's it. It's, seems like a lot, but it's pretty well structured. Yeah.
Can the F block hold 16?
Yeah, the F block holds not 16, 14. 14. Yeah. So, so this table, I think it's kind of screwed up. This should be here, and these two should be there instead. But anyway, you count it: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay. There's no better way to do it, because when you split the periodic table like that, they've got it should be kind of drawn like this. That's the way it really should be drawn. But that doesn't fit on a page, so. All right, so we did the numbers of electrons. We did the blocks. Like I said, there's a way to visualize it. So again, D block go down a number, right? So 3D, 4P. F block go down 2 numbers, because it goes from here, 6s to 4F, then to 5D, then to 6D.
I think I like the first way.
That's totally fine too, yeah. Like I said, that's the way I started learning it, and it's like stuck with me, so it works. Alright, so running out of time. What is the electron configuration for nickel? We have a little bit to go.
That's Ni.
Ni, nickel, yeah. Number 28. I'll give you a hint. Everything up to here, from here to here, is exactly the same. So you can probably assume that that's fine. So really you got to look at the last couple parts. Unless it's none of the above. Okay. We got a few votes in. Most people say D. Sorry, C. So most people said C. And it is C. So 4s2, 3d8, that's it. Because if you count over from the beginning of the row, it's 4s, 1, 2, and then 3d, 1, 2, 3, 4, 5, 6, 7, 8. So 4s2, 3d8. Now, there's going to be some exceptions. We'll come to the exceptions another day. There's always things that don't fit the rule that we just learned. But in general, that rule works really well, okay? Okay, we'll come back. Well, you'll still see problems like this again. Okay, so that last one, europium, was a lot to write. Doesn't even fit. So we, of course, as chemists, needed a way to abbreviate these. And so we have something called the noble gas notation. It's also called the condensed electron configuration. The way it works is, we've noticed, hopefully you've noticed, that, the beginning part is the same for a lot of these things. So we needed some standardized way to kind of, hey, say this beginning part is the same as something else. So we used noble gases as our kind of a shortcut. So if you look at sodium, the beginning part of sodium is exactly like the noble gas that comes right before it. So sodium is number 11. Right before sodium is neon. So what you can do is you can just say, well, sodium's electron configuration looks just like neon's. We write neon in brackets, square brackets. And then the rest of it is 3s1. So we basically just took that and abbreviated this part. So that's the condensed electron configuration.
And so, just to be clear, brackets are used to denote that it's not actually that element.
It's I don't know who started it, but that's the way we do it, yeah. So in an electron configuration, if you see a bracket around something, that's just saying it's the same as this. It's same as the electron configuration of whatever's in the bracket. Yeah.
Okay.
Usually it's going to, I think exclusively it's going to be noble gas. So here, calcium is just like argon, but with an extra 4s2 added to it. So how do we do that? Calcium, the noble gas that comes before calcium, go backwards is argon. And then we do the rest of it. We do it's 4s2. So same idea. You can still use the periodic table to kind of fill in the rest.
Well, potassium, K would be 4s1.
Yep, argon 4s1. Yep. Now, there is a little bit of irregularity in this in terms of what a professor who teaches chemistry will accept from a student in terms of an answer. If you were to just say the noble gas configuration of argon is argon bracket, technically you're right. It's probably better to give a little bit more detail. And the reason why it's not a great way is because there's another meaning behind square bracket. The square bracket also means concentration of whatever's in there. So by itself, it looks weird. It doesn't look like an electron configuration. So I'll accept it if it's obvious you're answering what is the electron configuration. But just be warned that some people will mark it wrong. All right. You have a question? You're just going to ask me about that. Okay. So you have to do electron configuration for magnesium and bromine. Here's the original. In the noble gas version would be, so for magnesium, right before is neon. So we swap out, wait a second, that's bromine, excuse me. For bromine, the one before is argon. So we swap out this whole thing with argon, and then after argon, 4s2, 3d10, 4p5. For magnesium, neon is the noble gas that comes right before it, and then 3s2. This is something you're gonna have to practice a little bit. You'll see it in homework. It's not hard. Once you get it, you'll get it. It's not that bad. We also have to include ions though. So electron configuration of ions. So again, you can have ions formed by adding electrons or removing electrons from the valence shell. And the electron configuration of ions is actually fairly easy in most cases. The cations, the positively charged ions, tend to look exactly like the noble gas that's right before it. And anions, so things that gain negative charges, gain electrons, tend to look like the noble gas that comes next. So for instance, calcium 2+. All right, regular calcium, regular metallic calcium is this with a 4s2 added to it, right? There's 4s2 on the periodic table. But at calcium 2+, those 2 electrons are gone. And now it looks exactly like argon, the noble gas that comes right before it. sulfide is normally, so sulfur is normally 3s2, 3p4 at the end. But s2 minus means you add 2 extra electrons, and so instead of 3p4, it's now 3p6, which is the same as argon. It's the noble gas that goes right after sulfur. So you're starting to see patterns, hopefully, of why these ions form the way they do. Something about those noble gas electron configurations that make them very stable.
Wait, so how do we write those? Or are you about to tell us that?
So this is where, you know, I could say, oh, what is the electron configuration of calcium? And then you would write, oh, argon 4s2. And then I'd say, well, we'll write the electron configuration of calcium 2+ now. And then you would say, oh, we'll just get rid of these 2 electrons. Argon. Which is fine.
Okay.
But like that answer, some other people would say, that's not enough information. You know, write out the whole thing.
I see. But if it's in a noble gas configuration like argon in this situation, could you put like neon 3s2 6p?
Yeah, you can
Or,
also definitely write
3p6.
like you said. Yeah, you could write neon 3s2 3p6. That's the same.
Okay.
Yep.
Very cool.
Or the full thing.
Sure.
Yep. Okay. One sample, one row here, real quick. What's the condensed electron configuration for boron? It's not much of a shortcut, but that's technically what one of them was, correct? Okay, so a little bit all over the place, but most people think it's D, and it is D. So to do it, again, you look at what's the noble gas that comes right before it. It's helium. And then we'll start from helium. Right, helium in brackets. After helium comes the 2s block with 2 electrons. And then we get to the 2p block, but that's where boron is, so 1 electron. 2p1. So 2s2, 2p1. This is not much of a shortcut, because what is helium's electron configuration?
Right.
1s2. I don't know what's easier to write, 1s2 or helium bracket. They're the same.
It would be one for helium. It would be 1s, 2s.
1s2. That's it.
Just 1s, 2.
Yeah. So helium has 2 electrons, and they're both in the 1s subshell. So 1s
Oh,
to the 2 power. Yeah. Yeah.
If we were doing nitrogen,
Uh-huh.
it would be helium, 2s2, 2p3.
Exactly. Yep. So here's one we'll do really quickly. What's the condensed electron configuration for the rubidium plus ion? Actually, might as well put the thing on here. You can answer it real quick. I think we'll be done close to this. So rubidium plus ion. What's the correct configuration? Okay, so we have equal votes for C and D, and I completely understand. The answer is C. D is original rubidium. It's krypton 5s1. So that's regular rubidium. It's got one electron in the s shell. Rubidium plus, that electron is gone. You don't write 0. You just leave off the subshell completely. And so here's an answer that is somewhat acceptable, but meaning I'll accept it, but some people won't. So that's it. That's what I want to talk about today. But let me tell you what we're going to talk about next. So we have this model that works really well to explain all the data we've talked about so far. It fits the data, so it's a valid model. But this model is very, it's simplistic in how we visualize what's happening with the electron. Electrons orbiting the nucleus, like planets orbiting the sun. The problem is that when we dive a little more deeply into how an electron behaves, and we're not going to get into the data because it gets really hairy, this model fails us when we start really looking at what an electron does. And I'm going to show you a video about weirdness of electrons, not today, next week. And it's going to be the basis at the beginning of why we start thinking of the electron not as a particle anymore, but just like we thought of light as waves only, and then suddenly we were like, oh, we got to treat light as a particle now, a photon. We have to do the same thing to electrons. So now we only thought of the electron as a particle. We're going to have to treat the electron as a wave also, which is weird, right? Where is a wave located? When you see a wave like this, where do you say it's located? There's no one spot, right? Where an electron is a piece of matter. You imagine it to be in one spot, but it really isn't. And that's how we're going to have to think of the electron. So electrons flying around the nucleus is not really the picture. It's more the electron is smeared in this volume of space around the nucleus. So that's the weirdness we're going to get into next. So that's quantum mechanics, where you start thinking everything as a wave, or both a wave and a particle, I should say. And our minds just can't visualize it very well. I mean, I don't know, maybe you have a creative enough mind that's better than I do. But it's where we have to turn to math, really. And we're not going to learn any of the math, don't worry. That's an advanced class, graduate level course. But so after this, we have to turn to pure math in order to describe what an electron is doing. We do have visualizations. We're going to see those. That's where the orbitals come from, those dumbbell shapes you might have seen. But we'll get to that next week. All right, so that's what we're leading into next. All right. Sorry, let you guys go.
Will this be on the quiz next week?
You should make it part of the quiz.
I could. Definitely the shells and the total electron spectra stuff.
Okay. Like the stuff from last Thursday on Tuesday?
Yeah, I mean, so everything for last week is kind of leading up to the stuff we covered today.
Okay.
So yeah, all that stuff.
Okay.
That bad boy's saying low battery.
Oh, okay. Thank you. If you want to ask me again on Tuesday, I can be a little bit more specific too. But I think for now, it's pretty much everything up to the quantum mechanics stuff. We're going to start next